This is a video about section 6.1, exponential functions. We'll talk about this for a few weeks, and I just wanted to give some intuition about exponential functions. So, defining an exponential function. An exponential function is anything that is described as multiplying by some growth factor every period. It might be, as in this example, a study found that the percent of the population who are vegans in the US doubled from 2009 to 2011. So it doubles every 2 years. And if we assume this rate continues, then you can, it was 10% in 2015, then it's going to be 20% in 2017, 2 years later. Then it's going to double again 2 years later in 2019 to 40. And then 180 or 80% in 2021 and 160% in 2023. Clearly, that's not sustainable. So exponential functions grow fast, like this example. So that's just a cautionary tale that exponential functions are usually only true for a short period of time, particularly in this example. It's clearly not true that 80% of the people are vegans at this point, but it doubled in one period. And so what you can do is think about exponential functions are anything that can be described as increasing by multiplying by something every so often. So it might double every 2 years. It might increase by multiplying by 1.4 every year. And that's an increase of 40%. So often it's a percent increase each year. And if it's 40%, then you'll be multiplying by 1.4, which is 100% plus 40%. So we'll talk about that more. So what exactly does it mean? So a percent change refers to the change based on a percent of the original amount. And exponential growth is a percent change every period. It might be every year, it might be every month, it might be every 2 years. They'll talk about that, and that will change the growth factor. So we'll talk about that as an example in just a second. You can also have exponential decay, which is if it's decreasing by a certain percentage each year. So maybe the value of a car is depreciating by 7% each year, and it repeats over and over. And so we're going to have examples where if it's an increasing function, we're going to have an r percent increase. You're going to multiply by 1 plus r over 100 as the growth factor. And so for an example of 5% increase, you multiply by 1.05 every period, whether it's an r percent increase every year or every month or whatever it is. You'll multiply by that every period. Similarly, you can have a percent decrease each time. And so that's going to be a 7% decrease would be 1 minus that percent. So 1 minus 7% is 93%. So you'd multiply by 0.93 every time. And the next year you'd multiply again by 0.93 and 0.93 of that. And you continue this exponential decrease. And it's important to compare the two between a linear growth and an exponential growth. So here's an example where you have two stores, and store A, or company A, looks like it's increasing by $50 each year, right? As 100, 150, 200, 250. That gives you a formula of the initial plus $50 per year. $50 per year is the increase. Right? And so after 3 years, they're up to 250. What about the other company where instead they're multiplying, instead of adding an extra 50 every year, they're multiplying by 1.5. So what that means is that's increasing by 50% every year. And if you increase by 50%, you multiply by 1.5 as the growth factor. And so in these two examples, that second year, they both gained 50 sales or whatever the idea is. Then they're up to 150. But by the second year, they've gained 50% of that larger amount. So they've gained more than the first company. And that exponential growth, because it's increasing on the increase, grows faster and faster and faster. And so you can write down a formula for this to be b of x is the initial amount times the growth factor raised to the number of years, the number of periods. So here's the formal way to think about that. The blue box is what they have in the book. An exponential growth grows by a rate proportional to the amount present for any real number x and any real positive numbers a and b. And b shouldn't be equal to 1 because that means the growth factor is 1 and your value is always equal to a. That's not very exciting. A growth factor or growth exponential function of that form, a is the initial value, because when x is 0, b to the 0 is 1. So f of 0 is equal to a times b to the 0, which is just a. And b is the growth factor. So you multiply every unit you increase, you multiply by another factor of b. In a lot of cases, we will have the growth factor based on some period. It might not be every year, it might be every 2 years or every 3 years or every half a year or something. And so often it'll be convenient to think about it in this terms. F is the initial value times some growth factor. And you multiply by that growth factor over and over and over again. And the exponent is the number of periods in your time period t. If t is years, it's the number of periods in t years. If t is months, it's the number of periods in t months, whatever that might be. And here's some examples of what an exponential function looks like. It starts off very small. The end behavior goes off to 0, off to the left, and it goes positive off to the right. It grows exponentially. And we'll talk a lot more about these details in the section. And here are some ideas you can note about the graph. The domain is all real numbers. The range is all positive. As x goes to infinity, the y value goes to infinity. As x goes to negative infinity, the y value goes to 0. It's an increasing function. It never touches the x-axis, and it has a y-intercept. Y equals 0 is the horizontal asymptote, and the y-intercept is 1. That'll be true in all of the kind of standard exponential functions that are written as f of x equals b to the x, right? So it'll change if transformations of that, but that's okay. We'll talk about that later. Let me give you one example in this video, and then we'll talk about it more on Monday. So in the book, the triad problem says a population of wolves is growing exponentially, and in 2011 there were 129. By 2013, there were 236. So it's growing at a rate of 200. So it's growing at a rate that goes from 129 to 236 every 2 years. So what did it multiply by to go from 129 to 236? It multiplied by 1.82. And so the idea is in an exponential growth, the population will multiply by 1.82 every 2 years. That's the 2-year growth factor. And so you can set up a formula for this. The number of wolves after t years is the initial amount times the growth factor. And why do we have t over 2 here? In t years, there's going to be t over 2 2-year periods. So for instance, in 10 years, you want this exponent to be 5 because they've multiplied by 1.82 5 times every 2-year period. And then we can do some algebra playing with exponents that we'll practice. T to the 1/2, you can bring that 1/2 inside the parentheses and take 1.82 to the 1/2 power. That's 1.35. 1.35 squared is 1.82. And so another way to express this function is here, where now we've changed the growth factor, the period of the growth factor, to be the annual growth factor. Every year, it grows by 1.35. That's a 35% increase. And if you do that twice, 2 years in a row, 1.35 times 1.35, that's 1.82. That's how we change the base to represent a different period, the growth factor for a different period. We'll do examples like that over and over again, and that will lead us to a way where we can solve these equations to find out when the population reaches 500, or what the population will be in 10 years,